Oscar Rodriguez is here today to share his interests and experience in deep learning inference in GNU Radio with ONNX. Please welcome Oscar Rodriguez.
Hi, my name is Oscar. I work at the Reds Department of HEIGBD University in Switzerland, and I will present you deep learning inference in GNU Radio with ONNX. As part of the initiative SDR Makerspace, we were looking for a solution that allows us to easily integrate deep learning inference and software-defined radio. Deep learning, it's getting more and more attention in the context of radio frequency domain, and we've seen very interesting work done with cognitive radio and optimal resource allocation. We've seen interesting work done in security with device fingerprinting, and there are many more other applications of deep learning in the radio frequency domain. And that's why we think that if we integrate deep learning at software-defined radio, we will have a platform that flexible enough that will allow us to easily test these kind of solutions for the radio frequency domain. We are also looking for an open source solution and be as flexible as possible, and that's why we have developed a GNU Radio out of the tree module that uses a standard format for deep learning model representation, and it integrates a deep learning inference engine. With the tools that we've chosen, which are ONNX and ONNX Runtime, we will have benefits as framework interoperability and hardware acceleration that we will comment further in the next slides. But we think that this provides, this checks all the boxes that we had. So we will discuss what ONNX is and why we have chosen it. ONNX stands for Open Neural Network Exchange, and it is an open format developed by Microsoft that it's built to represent machine learning models. And it's also an open standard that allows machine learning interoperability among different frameworks. Open format means that it can be used by anybody. Anybody can use the ONNX format in their own framework. Framework interoperability solves the problem that nowadays we have multiple and different and incompatible deep learning frameworks. So once you've chosen or you prefer to use, I don't know, Keras, TensorFlow, these are some of the deep learning frameworks that are widely used nowadays, you are tied to that framework. And you cannot move or choose another one if you don't, in an easy way, let's say. So with ONNX, we solve that problem, which is big nowadays if you want to provide with a flexible solution. As it is widely supported by most of the frameworks used nowadays, I will say by most of the most used frameworks nowadays. It's backed by big tech companies, so I think that they have enough support. And it's active developed by Microsoft, so they implement new functionality and they support new operations, and they release new versions very often. But it's not all good, and we have some cons. For example, there is some overhead of going from your preferred framework to ONNX. So you will have to adapt your model to ONNX, and that has a cost. And also operational availability, which means that not all operations are supported by ONNX, at least when they are released, and it might take some time. But that's not only the case. Maybe some custom operations are not supported, so we have a problem on operation availability. So basically, ONNX provides with a abstraction layer between our block and the different deep learning frameworks that are out there nowadays. So we can choose, or you can choose any framework, or at least one of the frameworks supported by ONNX, and then you can design and train your model in a MATLAB, for example, and then move your model into ONNX, so it can be used in our blog, and it can be used also by another inference engines and support ONNX. But in this case, you can go from MATLAB to ONNX, and you can go from TensorFlow to ONNX, you can go to PyTorch to ONNX, you can go from a lot of widely used frameworks nowadays to ONNX, and then you will have a common format for your machine learning model. Here, the different colors represent the different kinds of support that they have. For example, frameworks in green means that they have built-in support. So they have a small overhead to convert from that format to ONNX, but other frameworks, they need to use external tools, like this is the case of TensorFlow and Keras, which are also widely used nowadays. So there is, depending on the framework that you use, there will be more work or less work, depending on the support of ONNX in that framework. And basically, what ONNX does is it defines a common set of basic operations that are used by mostly in deep learning models. So you have basic common operations that you use in order to build a full deep learning model, and then ONNX defines their own set of these kind of operations. So for example, here in the image you can see how we have the same part of a deep learning model in TensorFlow and in ONNX. In the left, we can see that a convolutional operation in TensorFlow is translated into a convolutional operation in ONNX plus an activation function, which is in this case ReLU. So we can see that for TensorFlow, convolutional includes the activation function, but in ONNX is not included. And for example, a dense layer in TensorFlow, it's equivalent to a matrix multiplication in ONNX plus an addition plus an activation function. So this is how ONNX works. It defines these basic operations that can be translated to the other operations in other frameworks. Next, we have the inference engines that we have chosen. We've chosen to use ONNX Runtime, which is a cross-platform inference accelerator for ONNX models. It was built with the idea of supporting ONNX models by default, so it has a great support. It provides interfaces in Python and C and C++, which are mainly the interfaces that we care in GNU Radio, but it also provides other interfaces. It also supports different kinds of software and hardware accelerations, like libraries for algebra computations, or maybe hardware accelerations in GPUs, in FPGAs, in different kinds of hardware. And it also provides with an extensible architecture. This means that you can extend the inference engine, you can extend the ONNX runtime to support other hardware or other software acceleration or something like that. Here we can see that, as I said, what ONNX runtime provides us is an abstraction layer between our model and how you run the model. So for example, you have an ONNX model that can be run on a CPU, on a GPU. It can be run using a special library for deep neural network acceleration. It can be run in an FPGA. It can be run in an IRM CPU. So basically, it provides with an abstraction layer between the model and the inference. And here we have a high-level graph of the design of the ONNX runtime. Basically, what it does is it takes the ONNX model and reads it and makes it a representation in memory as a graph, where each node is a different operation, one of the basic operations that we mentioned before in ONNX, and then it assigns those operations to different execution providers. Execution providers are an abstraction for these software and hardware accelerations. So then it takes the input data and it uses the model in that input data, and then it produces some output. And here the extensibility comes from the execution providers. It means that if you can support a new hardware platform if you implement all the operations of ONNX in your platform, then you can include that as a new execution provider in ONNX runtime, and then you will have that platform supported by ONNX runtime inference engine. So now this is what we did. We have implemented a new radio out of the tree module that we call gr-dnn, DNN for Deep Neural Network. It's a sync module. That means that it will produce one output for each input, basically. We've chosen to use Python to develop it, using the Python interfaces of New Radio and ONNX runtime. This means that, for example, because we have a requirement by ONNX runtime to use Python 3.6 and above, I think, we have to use New Radio 3.8. We cannot use the previous version. And basically what our block does is it takes the input, and because New Radio doesn't have support for multidimensional data, it will adapt that input to the format expected by the model that you are using. Then it will feed the model with the transformed or adapted data, and it will read the output of the model and transform it back to a single dimensional format that it's written to the output port of the block. So, and it also provides with the different execution providers that are supported on an ONNX runtime environment. So you can choose to run the inference on a GPU or on a CPU or on other of the hardware acceleration providers that are supported in ONNX. So basically, to configure our gr-dnn block, you have to provide with the ONNX model, of course. Then you will have to configure the batch size, which is the number of elements that will be used at once to run inference. And this is to alleviate one of the problems of moving data around, for example, between an SDR device, and if you chosen to use the GPU for inference, you will have to move that data, and it will be more efficient if you do it in chunks of elements at the same time. So this is the batch size. Then you have to define the input size of one input flattened element, and the same is for the output. The output size is the size of one single flattened output element. We will explain it later with an example. And then you can choose the device that will be used for inference among the devices supported by the ONNX runtime installation that you have. So now we have prepared a small experiment to show up the capabilities of our block. We have prepared an example for automatic modulation classification, which is, you can find that example in different places. And we are using a paper from 2017 called An Introduction to Deep Learning for the Physical Layer by Timo Shi, where he proposes to use a deep convolutional neural network model for classification. You have the architecture of the model in the original paper. Then they use simulated data generated by New Radio for training. It's also available online, so you can download it. The input of that convolutional neural network will be a vector of 128 IQ values, and the output of the model will be the probability of that input for each of the modulations used in training. There you have a list of the modulations that they used in the simulated data. Now here we have the model that they use for classification. As I said, is a general diagram of the model, and is a convolutional neural network. The convolutional neural network, basically, it has an input, and then usually it has a convolutional part, which can be understood as a feature extraction part. Then you flatten that features, and then you run a full connected part in order to make classification on the feature extracted by the convolutional part. But this is not a talk about deep learning. It is based on a model called BGG16, which is a model used for computer vision, if I'm not mistaken. This model that is used in the paper, it's relative small compared with the models that you can find in the literature nowadays, but it's complex enough. I think that it has around 350,000 parameters. And this is the flow graph of our experimental setup. Here we are using a Pluto board as an SDR source, and then we take the output of the SDR, which is a stream of IQ values, and we represent it in a waterfall sink, so we can see the data that we have and the data that we are going to feed to our model. Then we take also that output of the SDR device, and we transform it in order to adapt it to the input of the model. As I said, GNU Radio doesn't support multi-dimensional data, so if your model requires multi-dimensional data, which is the case, a vector of 128 IQ values, you have to adapt it somehow, and this is interleaving the I and Q values, and then if you interleave 128 I values and 128 Q values, you will have a vector of 256 float values, and that's the input of our model. But this will depend on how you have designed your model, and this is a step that you have to be especially careful, because the adaptation depends on how you design your model. So then, as I said, the output of the model will be the probability of belonging to one of the modulations used in the simulated data. In this case, the list was the 10 different modulations, and we will use CUDA for inference. So then we will take the output of our block, and we will represent it in two ways. One is we convert it back to a stream and plot it in a time raster sink, which is kind of hard to understand, and then we will also take the output of the model and feed it to a UDP sink, so we can use external tools to represent the classification, the output of the model. Here we have the output that we will get inside GNU Radio, which is basically the waterfall with the raw data from the SDR device in the top, and in the bottom we have the time raster sink that we spoken about. Basically, to understand the time raster sink, you can find the time in the y-axis, and in the x-axis you will have the different labels used in classification. In this case, we are using 10 columns because we have 10 different modulations. So each column corresponds to one of the modulations that has been used for training. And the color in each time step in the y-axis represents the probability of belonging to that modulation. But as I said, this is kind of a messy way to represent the results of a classification. So that's why we are using an external tool, which basically what it does is it treats from the UDP socket, and then it represents the average probability of each of the modulations used on the training for one batch of elements. So here, for example, you have the mean probability on a batch size of 200 inputs of belonging to one of the modulations used in the model. So now some notes on performance. Deep learning inference is computational intensive, and it's quite expensive, computationally speaking, but it mostly depends on the complexity of your model. For the model that we have used, we don't have a very good performance using the CPU, but if you tune the batch size and you use hardware acceleration, for example, with a GPU, you can obtain real-time inference. And we even hit the bottleneck of the USB communication between the SDR device and GNU Radio. So now, in conclusion, we have implemented a new radio out of the tree module that can integrate that integrates deep learning inference and SDR. It supports a standard format for a deep learning model representation, and it supports different acceleration methods, hardware and software. We have shown how you can use this module to perform deep learning inference in a real scenario for digital automatic modulation classification, and you can achieve real-time inference using our block if you have hardware acceleration available and you tune up some of the parameters. But that's not all. We would like to keep up improving the block. For example, making it more flexible for different kinds of deep learning models, because you can have a variety of deep learning architecture that are not supported now in our model. For example, you can have multiple inputs and multiple outputs. There are a whole slew of deep learning models out there. We are considering including some of the functionality that you usually require in deep learning, like preprocessing inside of our block, so we can facilitate this kind of tasks in New Radio. We would like to include more examples, so you can see how, for example, you can use our block for denoising or other simple tasks like I don't know, binary classification. And also we have to keep up with the fast development pace of ONNX and ONNX runtime environment. Finally, here you have a link to our project where you can find the source code, because it's an open source and collaboration is welcome. You will find the documentation. You will find different examples, not only the one that we've shown here. And we also prepare some Docker images, so you can have an environment ready, like really easily. And now I will be, thanks for your time, and I will be glad to answer any of your questions.